Good morning, student. I welcome you in this special lecture on electrochemistry series. In continuation with my previous lecture that was based on electrical double layer theories or electrical double layer model, today I am going to discuss one of the most important electrical double layer theory, or even you can call it electrical double layer model, that is Gouy-Chapman model. If you gone through my first lecture related to the electrified interface, we have seen that there are three models. First model is Helmholtz and Perrin model. I will not discuss that model. And the second model is the Gouy and Chapman model. And third model is the Stern model. There are some problems in that Helmholtz and Perrin model. So Gouy and Chapman developed that model, which is more realistic than the Helmholtz model. Basically, in all these models, we derived the differential capacitance and the movement of the ions. In Helmholtz model, we have seen that there is no change in this capacitance, and it is just like a simple condenser model, and that potential gradient decreases sharply. Now, as you know, the name itself is a definition. This model was developed by two great scientists. One is French scientist Louis George Gouy, and he published a paper in French language in 1910. And of course, another scientist, Chapman, is from UK, and he also published a paper in 1930s. So therefore, we generally call the Gouy and Chapman model is 1910 to 1930. They studied the electrical double layer independently. And what was the main objective? Because you know that if we take an electrode, or sometimes we call it a charged surface, and dipped in an electrolyte, you know that if this electrode is positively charged, so due to this electrostatic attraction, there is a layer of negative electrode. But sometimes what happens due to thermal motion, there is a movement of the ions, and that how it describes how that ions are distributed near a charged surface in an electrolyte, and what would be the possible role of potential gradient. That has to be decided by that Gouy and Chapman model. And when interfacial capacitance of a metal electrode is contact with dilute electrolyte, it is explained by that model. And electrochemical double layer capacitor stores in the charge electrically. And I have already discussed about this Helmholtz model. Now, first question any student can ask, what type of parameters can be determined with the help of this Gouy and Chapman model? I must confess that this is one of the best, of course, theoretical model, and I must tell that it is a mathematical model, because there are some elementary mathematics, trigonometry or differential integral calculus we will use. So it is a of course, theoretical model, and you can call it a quantitative description of that electrical double layer at the interface between a metal electrode, generally हम उसको charge surface and that electrolyte, and ultimately we will determine change in electrode potential with respect to the distance, because when there is a movement of the ions from electrode to that a particular distance, how we calculate that change in potential with respect to distance, it is x. That parameter can also be calculated. Number two, we can also calculate the excess charge density. And again, excess charge density related to electric potential. That is called the capacitance. That can also be calculated in that model. In addition to that, there are many other parameters we can calculate. But one thing that here there are certain assumptions. I am not saying that this is the perfect model, because you know that the ions are having different sizes. But here we consider the ions are just like a point charges. So there is no size of that ion. So that is one of the assumptions. Now, if I just prepare a chart, so you can understand the point starting from the charged surface and electrolytes. Then, of course, there are coions and counter ions. So gradually that the counter ion disperse, and of course as it go on, जितना दूर उस इलेक्ट्रोड पे वो जाता रहेगा उसकी concentration भी कम होते रहेंगे, and ultimately there is a decrease in the potential. That we have to calculate this thing. And this, why we study this Gouy and Chapman layer? ये बहुत सोचने की बात है. Because you know that in any biological system, everywhere the distribution of the ions plays a very significant role in electrochemistry and biological process. Or in my first lecture regarding this electrified interface, I have discussed these things very categorically. And you know that there are some macromolecules like DNA or protein. So the role of potential gradient and equilibrium distribution of ions around that macromolecule is very important. So these are some application of that thing. Now I am coming to the diagram of this Gouy and Chapman layer. इसको बहुत अच्छे से आपको समझना है. Now you see that I am just talking about that the main problem is that d psi and dx. This is the main formula. Change in potential gradient with respect to the distance. If I just talking about this, the electrode, so where distance is 0, and there are certain, because it is I am taking a positively charged electrode, so there are certain negative anions are also there, but remaining anions are also dispersed. So there is a formation of diffused layer. So it is called the diffused double layer, and there are some hydration is also solvated cations, so that is different thing. So this part is an imaginary plane, laminar, I can conclude it. So here is x is equal to 0, where that chemical potential is 0, and when it moves here, so we have to calculate. And if you see the nature of this curve in Perrin model and Helmholtz model, there is a direct decrease, but it is exponentially decreased. So we have to calculate all these things. Now, point charge I have already told you. Then electrolyte contains the mobile ions, and we are in mind that the dilute type of the solution. And solvent is very important, because whenever we derive this whole equation, you will find that I have to use two parameters. One is dielectric constant of that medium, and one is epsilon 0 standard system. And ion distribution follow. When there is a distribution of ions की जब distribution होगा, diffusion होगा, so naturally we have to take the help of this Maxwell-Boltzmann distributions. So in simple language, how do I derive that Gouy and Chapman layer? Using two concepts. One is called the Poisson's equation. अब आप बोलेंगे what is Poisson equation? Poisson equation is a relationship between the potential gradient or electrical potential and the charge density. That is Poisson equation. And another is this Boltzmann statistic. And when you mix this Poisson equation and Boltzmann equation, it will be called as, you are all aware of all these things for every mathematics student, Poisson-Boltzmann distribution, which is a nonlinear differential equation. Okay. Now, the concept is that when you gone through some of the literature, जब आप literature देखेंगे, you will find that there is a similarity between the Debye-Huckel theory and Gouy and Chapman theory. आपके मन में प्रश्न आएगा कि Debye-Huckel theory was developed 1923, whereas Gouy and Chapman theory was developed in 1910. मतलब Debye-Huckel theory से 10 साल पहले इसका आविष्कार हो चुका था. So why we are talking about the Debye-Huckel theory? The reason is that when you see your prospectus course content in first semester, or even in, I think in B.Sc, I am here, you have already studied the Debye-Huckel theory, where we consider that there is a central ion and is surrounded by different ions, and how we calculate the force and other things using the Poisson-Boltzmann equation. तो इसलिए हम लोग Debye-Huckel थ्योरी, क्योंकि आप लोग फर्स्ट सेमेस्टर में और बीएससी में Debye-Huckel थ्योरी पढ़ चुके हैं, यू नो द Debye-Huckel, Debye लेंथ एंड अदर थिंग्स, देयरफॉर आई एम जस्ट कंपेयरिंग. अदरवाइज Gouy एंड चैपमैन थ्योरी 1910 में हुआ था और ये Debye-Huckel थ्योरी 1923 में हुआ था. Okay, and ultimately capacitance, you know that in Helmholtz equation is very simple, it's just like a simple capacitor like that, plus and minus, and there is a change, direct decrease like that. So you know that this is the formula of this thing, but don't worry about the Helmholtz equation. Now I am coming to this derivations. Now before that derivation, आपके मन में एकदम clear cut idea हो जाना चाहिए कि what is the difference between Debye-Huckel and Gouy and Chapman. But there is a relationship, because you know that there is a question of ionic cloud here. Same thing is also, there is a ionic cloud is also there, but it is a spherically symmetrical. In both the cases, we will use the Poisson-Boltzmann equation, but if you are a mathematics student, you can understand, because the concept is different. Here is a spherical, और यहाँ पे हम लोग बिल्कुल एक फ्लैट टाइप का ले रहे हैं मॉडल, यहाँ पे एक just like this and this type. So the mathematics may be different. Mathematics may be different. Here we will use some parabolic concepts and hyperbolic function and other things. लेकिन फिर भी आपको, but you know that there must be, sometimes we calculate the thickness of the ionic atmosphere. Sometimes it is called the Debye length, kappa. Here is also we calculate this. Now this change from psi is equal to 0 is equal to psi is equal to x, psi x, which is infinite almost. And these decrease can be calculated, you know, that finally we also determine this sine is equal to sine 0 exponential minus half x. So there is a relationship between this Debye theory and now you know that again it is hypothetical thinking that this is the electrode and definitely we will calculate the metal charge density, that is called the Qm. And you know that Qm plus Qd is equal to 1. So Qm is equal to minus Qd. So that is the total diffused charge density. And again same thing like your Debye theory, but spherically symmetrical वहाँ पे दिखाता है. तो वहाँ पे भी ये देखिए 1 by kappa Debye length, or here is also same thing. But there are certain steps. So step by step we have to derive. So therefore, why we need this QD, total diffuse charge density, number of charge changes with respect to distance per unit volume and other things. Because in order to calculate the differential capacitance, we need this value QD. So we have to determine QD. इसलिए आप कंफ्यूज मत होइए, इसमें बहुत सारे अलग अलग डेरिवेशंस हैं और फिर we will do a final derivation. Now frankly speaking that for mathematics students or the students of chemistry having the mathematical background, they can be easily can be understood the derivations. And I have referred large number of research papers, some Google search, some internet material, AI, NPTEL lectures, and some Indian books also. I thought that I must, it is my intention, and if you refer most of my lecture, मैं ये कोशिश करता हूँ कि the derivation must be student friendly, so that each and every student of M.Sc, second semester chemistry, are able to solve that Gouy and Chapman equation. But for notations and other constants, I have referred the best book, that is, you know, that Modern Electrochemistry by Bockris and Reddy, and part 2, second edition, Fundamentals of Electronics. And there is a chapter 6, and he has given all the information of this Gouy and Chapman model, but of course complete derivations are not available, but they have given the full concept of. So I request my students that they must refer this Bockris and Reddy. I have found another Indian book, that is a textbook of physical chemistry by Gill. Of course, they have given the complete derivation of Gouy and Chapman model. But again, as I have already told you, that it is up to you. Don't worry about this big derivations, but आप स्टेप बाय स्टेप उसको अगर डेरिवेशन करेंगे तो आपको समझ में आएगा. And it is not mandatory. If you don't understand the fundamental mathematics, you can directly write the first Poisson and Boltzmann equation, and then from Poisson and Boltzmann equation you can derive the change in potential gradient with respect to distance, and of course ultimately finally you have to derive the differential capacity and the role of potential with the distance. And again, it is up to you I am not saying that you blindly follow my derivation, but it is a student-centric derivation. You can do it. Otherwise, there are many methods. So you can derive as per the norms of the mathematics. Now, let me tell you that what parameters can be studied with the help of this Gouy and Chapman model. Now, this is the final derivation. I should write it number 1. Number 1. So, this is the number 1. The final derivation of Gouy and Chapman, and it is a quantitative description of potential gradient with respect to time 8 n0 Boltzmann constant T, sin 8 is related to hyperbolic sign, and then Z charge, valency potential 2 kVt. So it relates the electric field and the potential at any distance. So this is number 1. Number 2, or finally, we have to determine the QD, total diffused charge density. So this is 1, this is 2. And number 3, the differential capacity. You know that I am not talking about how we define the differential capacity, or in some books it is written like differential capacitance भी आप बोल सकते हैं. और ये अगर आप देखेंगे, ये देखिए यहाँ पे, because I am talking about the diffuse layer, so change in diffuse with respect to potential gradient. तो मैं हिंदी में आपको समझा रहा हूँ कि गाउ एंड चैपमैन थ्योरी में हमको फाइनली 3 डेरिवेशन आपको निकलेगा. आपके ऊपर है, आप अगर उसको नहीं समझ सकते तो आप एक ही डेरिवेशन कर सकते हैं, लेकिन फाइनली हमको कैपेसिटेंस को निकालना है. बिकॉज इफ आई वांट टू वैलिडेट दैट गाउ एंड चैपमैन लेयर, आई हैव टू प्लॉट ए ग्राफ बिटवीन द कैपेसिटेंस एंड पोटेंशियल. तो किस तरह से आएंगे डिफरेंट कॉन्सेंट्रेशन, दैट इज ए sometimes getting inverted parabola, different type of the concentration. तो ये 3 डेफिनेशन आपको समझना है, और इन तीनों डेफिनेशन को करने के लिए the weapons or the vehicles is nothing. One is Poisson equation, another is the Maxwell-Boltzmann distribution. If I mix it, blend it, so it will be a Poisson-Boltzmann equation, and we have to integrate that Poisson-Boltzmann equation. We will get the final equation. Do I make my point clear? Okay. Now I am just coming the first point, that again and again I am just considering the point charge. So there is no definite size, and the Poisson equation is like that: del square sine dx square is equal to rho epsilon r epsilon r. इसमें भी आप कंफ्यूज मत होइए, बहुत सारे बुक्स में आप देखेंगे रो x. For mathematical simplicity, I can use the only epsilon, and that epsilon is equal to epsilon r and epsilon e. Now that ER, it is the actual relative permittivity or dielectric constant of that medium, because you dissolve some of the electrolytes, and the E0 is the permittivity of the free space, and I have forgotten the value, which is very low, 10 to the power minus 12 like that. तो अगर आप डेरिवेशन में पॉइजन इक्वेशन में रो इप्सिलॉन भी लिखेंगे तो कोई प्रॉब्लम नहीं है. एंड व्हाई आई हैव रिटन एक्स, बिकॉज अगर हम डिवाइड का करेंगे तो एक्स डायरेक्शन, वाई डायरेक्शन, जेड डायरेक्शन, लेकिन यहां पे वी कंसीडर just like a hypothetical system lamina, and the ions are moving into one direction, only one direction. So that is, therefore I have written here x. Okay, and I have given the units, don't worry about the units and other things. Now second question is that, so you know that about the Poisson equation, there is no problem. Now this is del square sine x square minus rho x and e. So I have to calculate this distribution. So the distribution is again in all know, मैं बहुत बार आपको मैक्सवेल बोल्ट्जमैन डिस्ट्रीब्यूशन स्टैटिस्टिक्स, पूरा स्टैटिस्टिक्स आपको पढ़ाया हूँ, स्टैटिस्टिकल थर्मोडायनेमिक्स. So it is very simple, just like in normal cases, ni n0 exponential ei by kt, k is Boltzmann constant. But here you know that we are talking about the electrical potential, you know that is equal to EMF and other things. So therefore it is valency, then the charge of the species and this electrical potential, and it is Boltzmann constant and T. Again bear in mind there are cations as well as anions. But here I am written a simple case. In some book N0 of I species, this Ni is the total concentration. In some books it is also written, अगर आप C0 भी लिख सकते हैं, पर यहाँ पे हमने N0 करके हम लिख रहे हैं, bulk concentration of the species, and Ni is that number of diffuse ions, Now in order to calculate the relative charge density, because there are positive ions, co-ions, counter ions, so in order to determine this is for cations, same thing, exactly same, because there is no change in N0 or P0, only where there is a change, some cations and anions. Why it is negative? Because you know that cation charge negative, but here why it is positive? Because it's anion, so one is positive, same thing you see here. Clear? So one is for cations, another is for the anions, positive ions and negative ions. So I have to substitute this value in this equation. Come on, this point. So relative charge density is equal to summation Zi charge. Again bear in mind that I am, for this simplicity and clarity, I am using symmetrical system where I consider that Z plus is equal to Z minus, like sodium chloride. So one univalent electrolyte. So it is a very simple cases. So that means whatever this Nx and N minus. Now there is a question of the trigonometry, because when I use this thing, that is I can use like that exponential, it is minus Z E sine kBt minus exponential Z. It can be common also. Here is plus divided by kBt, like that. Or even Z, we can take the common part, and this is the, suppose this is the x, this is the x, or even a. So exponential minus a minus exponential a, that can be solved, and this, if I want to solve it, this is actually, we need the hyperbolic sine. So it is actually sine h hyperbola or e. So sine h is equal to this exponential minus exponential a divided by 2. It is a simple trigonometric mathematics. So if I write like that, I am getting this is common part and this part is rho part. And also hyperbolic sine function, and from that we will get this 2n0 Ez Er Eo and sin. आपको कठिन लग रहा होगा, बिल्कुल कठिन नहीं है. मैं आपको इसको how can I get this thing again and again? I am just repeating this thing for the students' clarity. This is del square sine dx square is equal to minus rho x e 0 and er. So this is er and e, and that rho I am taking from that Maxwell-Boltzmann part. तो यहाँ पे हमने लिखा. अब इसको साइन कहाँ से आया? जैसा why it is called, this h is called actually hyperbolic. साइन हाइपरबोलिक कहाँ से है वो मैंने अभी आपको बताया. ये एक्सपोनेंशियल माइनस ए एक्सपोनेंशियल ए. Here z is common, e is common, n0 is common. Agreed? Here is for cation, here is for anion. So I थोड़ी देर पहले ही मैंने आपको बताया कि it is hyperbolic sine exponential a minus exponential 2 sine a k. This is a formula. There is no confusion with that. अगर आपने यहाँ पे e माइनस ए अगर किया, e माइनस e प्लस किया, दिस इज इक्वल टू माइनस 2 साइन ए, और ये आप बोल सकते हैं साइन ए डिवाइडेड बाई 2. So that in place of exponential, if I take the exponential and add it, you will get 1. So this एक्सपोनेंशियल के जगह में घबराने की जरूरत नहीं है. क्या आएगा? सीधा हम लिखे माइनस 2 साइन हाइपरबोलिक ए. सो जस्ट आई वैल्यू हियर 2, z is a common, e is common, n0 is common, and the sine a z d b. So it is a, अब इस वैल्यू को हमको कहां पे सब्स्टिट्यूट करना है? हमको पॉइजन इक्वेशन में सब्स्टिट्यूट करना है. फिर से समझ लीजिए पॉइजन इक्वेशन में फिर से आपको बार बार एक ही चीज को बता रहा हूं. ये डेल स्क्वायर साइन dx स्क्वायर माइनस रो एक्स ई आर ई. अब यहां पे भी माइनस है, यहां पे भी माइनस है, तो इसलिए माइनस माइनस कैंसिल हो गया, प्लस हो जाएगा. एंड E0 एंड ER की वैल्यू आप इसको E भी लिख सकते हैं, इसमें कोई कंफ्यूजन नहीं है. तो देखिए माइनस माइनस कहाँ चला गया दोनों, तो ये वैल्यू हमने ये माइनस और उसके माइनस को कर दिया. तो डेल स्क्वायर डी साइन, ये मेन इक्वेशन है, इससे अब आगे हम डेरिवेशन करेंगे. तो 2ZEN0 द कॉन्सेंट्रेशन साइन एच ZE साइन AB. यहाँ तक आपको समझ में आया? Those students who are not well aware of simple mathematics, they can directly write the Poisson-Boltzmann equation, and we have to integrate it, and we get the final equation. So again, I am just doing nothing. I have first written the Poisson equation, which relates the potential and the charge density. Charge density I calculated with the help of Maxwell-Boltzmann distribution, and then ultimately I am getting this value. अब आगे डेरिवेशन के लिए इन प्लेस ऑफ बार बार अगर मैं इप्सिलॉन लिखूं, इप्सिलॉन आर लिखूं, इट इज बेटर टू आई मस्ट राइट ओनली सिंपल इप्सिलॉन. फॉर टाइपिंग में हो सकता है कई जगह में आपको टाइपोग्राफिकल मिस्टेक होगा. आई एम ऑलवेज यूजिंग के सबस्क्रिप्ट बी विच इज बोल्डमैन कांस्टेंट. अगर कहीं पे ए बी पास पास आ गया तो आप उसको ओके. अब लास्ट स्टेप में आ जा रहे हैं. नाउ ये थोड़ा समझने की है, आपको थोड़ा समझना पड़ेगा. नाउ आई एम गेटिंग दिस फाइनल वैल्यू. नाउ आई हैव टू इंटीग्रेट इट. But before integration, I'll do some very little bit mathematics. You know that it is a non-linear differential equation because that sign is in the exponential part is also there. So what I do, if I multiply both the sides with that d sine and dx, okay. So this is, so I am getting what? I am getting d square sine, वो simple mathematics है, dx, d sine and dx. Now suppose this d sine and dx को मैं मान लिया u. You follow my point? d sine by dx को मैं मान लिया u. So and so u, फिर हम क्या लिख सकते हैं? अगर हम इसका du dx अगर हम करेंगे, du dx करेंगे तो ये हो गया del स्क्वायर साइन dx स्क्वायर. मतलब हमने क्या किया? इसका du कर लिया तो दिस वैल्यू हो गया. So that means what I can write here, it is actually du dx is equal to del square sine dx square, and I can write this is u du dx. लिख सकते हैं ना हम. और हम इस क्या लिख सकते हैं? u स्क्वायर du dx. इसका अगर हम डिफरेंस करें 2u du dx, और u इज इक्वल टू हाफ u स्क्वायर du dx. हाफ, ये देखिए हाफ. u स्क्वायर मीन्स डेल स्क्वायर dx, क्योंकि हमने du dx का निकाला, एंड u इज इक्वल टू सिंपली d psi by dx. So this is, so what I can write in place of del square u dx की जगह में हम लोग इसको वेरी सिंपल हाफ d से dx d sin upon dx लिख सकते हैं. So that Poisson-Boltzmann equation can be remodified. So half dx du, then remaining thing is same thing. Why I am doing all these things? Just to integrate it. Just to integrate it. अगर आपको नहीं समझ में आएगा तो मैं फिर से आपको इसको समझा सकता हूँ कि du dx को आपने u माना, इसका अगर हम डेरिवेटिव निकाले du dx का तो del square sin. So that means I can what I can write, it is actually mu square d to u. उसका अगर चेन रूल इसको बोलते हैं, चेन रूल. Very simple. Now once I solve this part, that means half, देखिए इसको अच्छे से देखेंगे. Now again, you know that integration of sin x is equal to cos x, like that. But here these are constant, तो इसको हमने बाहर रखा. Sin h, this thing. Suppose this, हम इसको इंटीग्रेट करेंगे sin h, इसको हम लोग ax मान रहे हैं. a, that means a is equal to z e sin kbt. And you know that ये क्या होगा 1 by a cos ax, बिकॉज इसको हम ये माना ना x माने इसको. जनरली हम क्या करते हैं इंटीग्रेशन ऑफ साइन इज इक्वल टू cos, बट हियर दैट इज फंक्शन z e, तो इसको हम लोग x a मान लीजिए x. तो क्या हुआ sin a इज इक्वल टू 1 by a cos a. a इज इक्वल टू z, a अगर हम नीचे रखेंगे तो दैट इज 1 डिवाइडेड बाई z e psi डिवाइडेड बाई kbt. तो कहां पे kbt फिर ऊपर जाएगा. So I am getting half, you see here 2z, ये तो कांस्टेंट है. kbt ऊपर कहाँ कैसे चला गया आपने समझे 1 by a means z e sin, तो ये ऊपर चला गया एंड साइन की जगह में ये cos हो गया एंड देन देयर इज इंटीग्रेशन कांस्टेंट, so there is no limit. So what I am getting half del square d sin square dx square is equal to 2 n0 kbt epsilon cos h jdc. तो अब जानते हैं कि अब इंटीग्रेशन जब हम करते हैं there is the integration cost, so determination of that integration constant and how we integrate it, because ये x हम मान के चले गए यहाँ पे चले गए and that sign is gradually converted into infinite like that. So that means if I'll do such type of things, so that is called the boundary condition, determination of the integration constant. This is our actually, and I have to determine the c. I have to determine the c and x. If x tends to infinite, sin is equal to 0, so naturally d sin dx, this whole part will be 0. Here is also 0, cos h 0 is equal to 1, because cos 0 h, cos h is 0. Here is 0, that is equal to 1. So what we will get? I will get only 2 n0 kbt epsilon c is equal to 0. So c is equal to minus 2 n0 kbt and epsilon. So what I am getting? C is equal to minus 2 n0 kbt epsilon. So now I have to substitute this value of c in that part. Okay. Little bit mathematics is, I am sorry that there are such a little bit mathematics is required, and practice makes perfect. If you do it, so you will get it. Absolutely no problem. So I am getting the values of c and I substitute the values of c here. Just for clarity, I am using different types of color so that students don't get confused. So here it is minus, it is common, you see here. This part is common. So what I can write? Half d is equal to 2 n0 kbt epsilon cos h minus 1. You follow my point? And then finally, because as I told you that ultimately our objective is the determination of t sin dx, change in potential with respect to distance from the electrode. And here I am getting the square. So I have to do the square root in order to get this. So last step. So this is the things. But again there is a, again I'll avoid that mathematics, that there are certain system that is called the hyperbolic identity. So you have to cram it. Due to shortage of time, I will not explain here because chemistry is chemistry, mathematics is mathematics, but there is a system, because here it is actually, if I just again if I consider it as a u, this is a u. So I am getting cos hyperbolic function u minus 1 like sin square plus cos square. There are so many formula and this is standard formula. So cos u minus 1 is equal to 2 sin h square u divided by 2. So you see here in this place I can write 2. So 2 into 2 4, 2 into 2 4, 4 into half this side, so 8. Then again n0 same, kb t epsilon sin h square. So now you can tell me, actually hyperbolic function are built from exponential terms, and when we square and subtract them, almost everything cancel out, leaving only 1. So what I will do it, del square dx square, just that. You see here, yes. So just you under root it, like sin h square. This value is suppose x. So we'll get sin 8x under root. And here del x square under root square. So we'll get the final result. Yes. These are equation. I just underroot it. Because ultimately our objective is, as I बार मैं आपको समझा रहा हूँ, ये पोटेंशियल ग्रेडियंट x के साथ यही एक्चुअली गाउ चैपमैन का फाइनल इक्वेशन है. तो डी साइन डी एक्स ये अंडर रूट हो गया 8 n0 kbt और साइन h स्क्वायर ये. सो दिस इज द फाइनल. अब आप बोलेंगे व्हाई यू हैव पुट इट इज मे बी प्लस माइनस, because negative sign is the chosen because the potential decreases away from the surface. It is exponentially decreases. अब कैसे उसको कैलकुलेट करना? So the first part is over. Let me again explain this thing. I have done nothing. First part is that I am using the Poisson equation and Maxwell-Boltzmann statistics. Apply these values of relative charge density, and then finally, of course, there are certain trigonometric terms and other things, some integration, some differentiation, and ultimately I am getting that final equation. Now the elementary part, that second मैंने आपको क्या बताया था, हमको निकालना पड़ेगा QD, टोटल डिफ्यूज चार्ज डेंसिटी. क्यों इसकी जरूरत पड़ेगा? क्योंकि अगर हम QD कैपेसिटेंस निकालना है तो इसमें भी हमको QD की वैल्यू को निकालना है. माय नेक्स्ट पार्ट इज द डिटर्मिनेशन ऑफ QD. ओके. सो अगेन in order to determine the QD, again I need, like Poisson equation, there is another law that is called the Ghosh law. Because now there are two parts, total diffuse charge and variation of potential with the distance. So that is very simple, that QD is equal to epsilon 0 d psi and dx. Again here is also you can directly write epsilon, कोई problem नहीं. So एकदम सिंपल है. We have already determined the d psi and dx की वैल्यू अभी देखिए. You have to substitute the values of ये वैल्यू निकाला. इस वैल्यू को आपको गॉस इक्वेशन में लगा देना है. ये यहाँ पे. तो ये देखिए ये दोनों अंदर आ गया. 8 E0 N0, ये हर जगह में अगर मैं k लिखा हूं तो इसको k भी कर लीजिएगा. मेरे टाइपोग्राफिकल मिस्टेक में फिर से कन्फेस, इट मस्ट बी KB. Now you know that again a simple mathematics. If I write here h under root of h, तो ये आप समझते हैं, ये हम ऐसा लिख सकते हैं ना, अंडर रूट ऑफ 2 only 4 into 2 लिखा हमने. So it is what 4 into 2 is 8. So what I can write under root of 2 और बाहर से 2 से मल्टीप्लाई कर देंगे. So I am getting this 2 epsilon E0 N0 kBT half or sine 8 by 8. So this part is over. That means I am getting that sine D. अब क्या करना पड़ेगा? कैपेसिटेंस निकालने के लिए इसका QD with respect to D sine. So the next part is that differentiation of QD with respect to. So determine the total diffuse charge density. The Gaussian box should extend from a place very close to the electrode, because we consider that this is electrode positively charged. यहाँ पे थोड़ा सा नेगेटिव चार्ज है और यहाँ पे चले गए आपका, where x is equal to infinite, because there is no delta x is equal to 0. Potential 0 हो जा रहा है. The total diffuse charge density is distributed throughout the solution due to the combined effects of the thermal motion and electrostatic forces. And I am taking from that statement from the modern electrochemical Bockris and Reddy. And this is the difference between the Helmholtz layer and the Gouy and Chapman. Helmholtz layer में कोई thermal motion नहीं हो रहा है. So now before doing this variation of potential with distance, you know that there are certain assumptions, because you know that if these values of ZE sine divided by KBT, everywhere मैं अगर भूल गया हूँ तो लिख दीजिए greater than 1. तो यहाँ पे there are certain approximation that sin hx is equal to x. So I can avoid these values of sine. I can avoid the values of sine. Sin h kdx kdt. आपका इक्वेशन एकदम छोटा हो गया, बिकॉज ये पूरे पार्ट को आपने x के बराबर मान लिया. साइन एच इज इक्वल टू, तो आपका इक्वेशन ये साइन का हट गया. तो व्हाट आई कैन राइट, देखिए छोटा हो गया इक्वेशन, डी साइन डी एक्स, बिकॉज दिस वैल्यूज ऑफ जेड ई केवीटी ग्रेटर देन ए. तो ये वैल्यू आपके पास. तो यू सिंप्लीफाइड इट. देयर आर सर्टेन कांस्टेंट को आपने बाहर निकाल लिया, z को भी बाहर निकाल लिया, इसको भी बाहर निकाल लिया. तो ये 8n0 kb, अगेन आई एम सॉरी इट मस्ट बी के सबस्क्रिप्ट, नॉट पास में नहीं होगा ना, सबस्क्रिप्ट है. यहाँ पे भी पास में हो गया ये, प्लीज ये होगा के बी, यहाँ पे भी होगा ये टाइपोग्राफिकल मिस्टेक. ये सबस्क्रिप्ट, डोंट से दिस सेपरेट. सो अगर हम इसको अंदर लेंगे, देखिए इट इज वेरी सिंपल. इसको अगर हम अंदर लेंगे, 2 के जगह में क्या हो जाएगा भाई, 2 बाहर आया, इसको अंदर अगर हम लेंगे तो ये 4 हो जाएगा. के टी के बी स्क्वायर बी टी स्क्वायर. सो दिस 4 डिवाइडेड बाई 8 2, एंड जेड को भी अंदर लेंगे तो ये जेड स्क्वायर एंड ई स्क्वायर. नाउ दिस के बी 2 where this cancel. So what I am getting, minus sine 2n square z square e square e0 kt. जब जस्ट थोड़ा अपने दिमाग में जोर लगाइए. अगर आपको डिवाइकल थ्योरी याद होगा, जहाँ पे वी डिटरमाइन दी डिवाइस लेंथ और द थिकनेस ऑफ द आयोनिक एटमॉस्फेयर. तो दिस टर्म 2n0 z square e square is the charge of the E0 kBT is nothing but the K. your kappa. You see this part, this part, this part. So now I have to just integrate it and rearrange this thing. Starting from the linearized equation. Now it is not non-linear Poisson equation, it is linearized Poisson equation because it is यहाँ पे kappa sin d sin dx minus. So rearrange कर ले because it is sin to sin d like dx upon you write like dx. You just take it a constant like that. So now integrate it. You know that 1 by x dx is equal to log x. 1 by x dx log x. And this is x. It is like all part is constant. This is z, this is k kappa. So finally, I am getting natural log of 1 by x dx log x like that. Dx, very simple integration. X plus again c boundary condition. We have to apply boundary condition. So I am getting natural log potential x minus 2n0 z square of x. Now you know that again we are considering the same condition that psi is equal to 0 because when it is the exponential change here. Here x is equal to 0. Psi. That psi is equal to 0. So we just integrate it very simply manner. We see that log natural psi k psi plus c and applying the boundary condition that psi x is equal to 0 first condition and psi is equal to psi 0 at infinite valuation. So there like just like that. Here is potential x0, x is equal to 0. Here psi is equal to 0, psi x, psi 0. So substitute the value and you very simple things and use the value of if it is 0. So k0 is equal to c, c is equal to log psi and ultimately you know that natural log of psi is equal to minus k kappa x. So, you know, very simple. Exponential minus kappa x. This is another equation finally. So we are getting psi is equal to psi 0 is equation number 2. This is kappa is again and again just like 1 by k dy length. So therefore this part actually again and again I am saying these changes can be calculated like that. Psi is equal to psi 0 exponential kappa x. Very important point. And this distance between these two is kappa inverse 1. Now the last equation. So first we determine the d psi upon dx. Second we determine the psi and this thing. Now last part is that the differential capacity. Now again आपको बहुत exhausted लग रहा होगा कि बहुत सारे डेरिवेशन इसमें है. तो अगर आपको चाहेंगे तो केवल फर्स्ट डेरिवेशन को ही कर देंगे. अगर आप डिफरेंशियल कैपेसिटी नहीं निकालना चाहेंगे तो भी कोई प्रॉब्लम नहीं है. बट डिफरेंशियल कैपेसिटी कोई कठिन नहीं है बिकॉज वी हैव ऑलरेडी डिटरमाइन द वैल्यू ऑफ टोटल डिफ्यूज चार्ज लेयर. So it can be obtained by differentiating the following equation with respect to potential. क्योंकि इसकी वैल्यू जो है ये Q d ऑफ साइन. ये वैल्यू हम लोग वहीं से निकाल चुके थे यूजिंग गॉस इक्वेशन. तो Here we use Poisson equation, Gauss equation, Maxwell-Boltzmann equation. So I know this value is there. Again, I must write here KBT. I must write here KBT. So this is the value. And however, in this equation, the variable is sign 0 because the potential at x is equal to 0. Therefore, we can write change in potential with this thing. This is the assumption. क्योंकि आपने देखा ना एक्सपोनेंशियल डिक्रीज हो रहा है इन्वर्टेड कॉस से करेंगे. सो डिफरेंशिएशन इज वेरी सिंपल. आप ऐसा कर सकते हो, इसको आप पूरे को आप कांस्टेंट मान सकते हो. ए आप कांस्टेंट मान सकते हो और इसको भी साइन एच ए कर सकते हो. तो डी बाई डी एक्स ए डी बाई डी एक्स लाइक दैट. ये जैसा मैंने बताया आपको कठिन नहीं लगेगा. ये देखिए डी क्यू बाई पूरे ए को व्हाट इज ए इज, क्योंकि आप लोग थक गए होंगे इसलिए मैं बहुत ज्यादा मैथमेटिक्स नहीं कर रहा हूं. ये पूरे पार्ट को मैंने ए कर दिया. दिस फुल पार्ट इज ए बिकॉज इट इज कांस्टेंट पार्ट एंड दिस पार्ट आई हैव टू जस्ट डिफरेंशिएट इट. यू नो दैट साइन का कॉस. सो ये देखिए जब हम इसको करेंगे तो इसका रिजल्ट आएगा ए. फिर वही है कॉस ए बाई एक्स. ए कॉस एच एक सब केबीटी है ना, केबीटी. सो व्हाट आई एम डूइंग व्हेन आई डिफरेंशिएट इट, जहां पे मैं इसमें डायरेक्ट वैल्यू लिख दिया हूं आपको सो दैट आपको कोई कंफ्यूजन नहीं होगा. और ए 1/a. So differentiate with respect to potential. So this is the final value minus dqd sin m is equal to 2e0 z square is n0 kbt. Again it is small kb, k and b and cos this part ready. Why I have written this psi m? आप देखिए पहले जो फॉर्मूला मैंने आपको दिखाया था, वन इज डिफ्यूज चार्ज डेंसिटी मेटल इलेक्ट्रोड एंड इट इज डिफ्यूज चार्ज डेंसिटी आफ्टर डिफ्यूज लेयर. सो आई विल गेट दिस फाइनल इक्वेशन एंड दिस इज एक्चुअली सी. इसको आप डिफरेंशियल कैपेसिटी बोलिए चाहे इसको आप डिफरेंशियल कैपेसिटेंस बोलिए. सो हाउ आई वैलिडेट दिस थिंग व्हेन आई प्लॉट ए ग्राफ between the capacitance with this potential difference with different concentration. So you see that this is high concentration and low concentration. It should, if I change the concentration, there must be some increase or decrease, but here sometimes maximum or minimum we are getting. When I have seen that book of that Bockris and Reddy, that capacitance and potential, so I said just like such type of curve is also higher concentration and lower concentration is also like that type of things is there. And they also perform some experiment. I am not showing all because the M.Sc second semester students who are not worried about the research activities taking by the different concentration of dimethyl acetamide and mercury electrodes and calculate the capacitance and other things. But validity is that there is a cos h function inverted parabolic dependence, and there are different. If you read large number of research papers, you will get different. Now, let me summarize the things. Today, I have tried to solve the Gauss-Chapman equation using some mathematical model, because it is a quantitative description of change in potential with respect to the distance of the ion or diffuse layer from the thing. Of course, it is one of the best model when we compare with that Helmholtz and Perrin model, because that time what was the observation that there is no change in capacitance, constant. But here you have seen that there is a change in capacitance, minimum or maximum like that. But the most important drawback is that in addition to the diffusion, dispersion, there may be some absorption. Some ions are absorbed on that electrode surface. Second, we are considering that these charges are point masses, but this is not the true. You know the different ions have a different size. So further modification is required. And the great scientist Otto Stern, who is a Nobel laureate, who modified this theory, Gouy and Chapman theory, and give this more realistic situation where he considered the compact layer, because here there is no compact layer, that is a diffuse double layer, compact layer as well as the diffuse double layer. He considered the inner Helmholtz plane as well as the outer Helmholtz plane, and finally determined the using the Helmholtz model and this Gauss-Chapman model, he produced the final model. So in my next, and thank God that if you compare the mathematical derivation of Gauss-Chapman and Stern layer, of course, the Gauss-Chapman layer, the derivations are simple. But for Gouy and Chapman layer, there is no alternative. We have to learn little bit of mathematics, some integration and some differentiation. Deliberately, I am avoiding some of the mathematical part, and I hope that you enjoyed this thing. But do practice, and step-wise you can determine various parameters. These are the application of this Gouy and Chapman. Otherwise, you can determine up to the change in potential gradient with respect to distance. That's okay. Thank you very much.